Hi, IBSL2. We are getting into our last 2 days before your test, and today we are going to talk about the second derivative, exactly what it sounds like. Once you guys take the first derivative, we have talked about how the first derivative really is your rate of change. So we've talked about how it's dy dx, the notation for it. F prime dy dx, slope of your tangent line, remember, because that's the way that we approximate it best, is the limit as you pick points that are closer and closer to the point you actually want to find the slope of. So slope of your tangent line. And then also we talk about it as, let me pull this down just a bit. And we started this whole unit by talking about it as a rate of change. So I'm also going to say rate of change. Well, of course, if you guys think to physics, if we're talking about a rate of change, what we're really talking about is a speed. So I'm also going to tack on here speed. All right. One other vocab word that is missing from this long list is gradient. Gradient is another word that we use for slope, all right, of your tangent line. So now this is a collection of every single way that we have described what a derivative is. If I ask you to find the slope of the tangent line, you find the first derivative. Rate of change, first derivative. Speed, first derivative. dy dx, first derivative. These are all different ways of finding a rate of change or a first derivative. So if I'm going to take a second derivative, what really is it, right? If I want to take a rate of change again, but I'm taking now the rate of change of my speed, because here my speed is my first derivative. So if I take a second derivative, what I'm really doing is taking the rate of change of my speed. If you guys think about that, let's say you're driving a car and you're driving at a certain speed, and then your speed is changing. Well, what's the rate of change that your speed is changing by? This is known as your acceleration, right? How much weight are you putting on your foot when you're speeding up, when you're pushing on the accelerator? So that's why that's called the accelerator. We're finding an acceleration. So we are now talking about the rate of change of your speed. And really, that's your acceleration, okay? So in words, we're really now finding an acceleration when you find the second derivative. Well, as you can probably tell already, a lot of word problems are going to come into play here in the next couple days. Tonight especially, and then also in class and in our, there we go, and then also in our day before the test. We're going to be reviewing a little bit of how we work with speed and acceleration. So notation, very similar. All right, we use the double apostrophe for the second derivative. I'm right here now. Notation for second derivative is f double prime. We also use the dy dx. So we are now taking the second derivative, okay, with respect to x. So all these different notations mean second derivative. How do I actually find a second derivative? Well, very similar to how you found the first derivative, right? If I'm going to, there we are. If I'm going to take the first derivative, so I'm going to go back in blue here. Blue was all my first derivative stuff. If I'm going to take the first derivative, which is f prime, I'm going to use my power rule. So let's look at the example I gave you guys here. 2x cubed minus 3x squared minus x plus 5. So my first derivative is straight power rule here. I have a polynomial. 3 times 2, I've got 6x squared minus through, let's go back. Forgot to bring down. Let's multiply the exponent. So 2 times 3, I get my 6. And then minus 1. Remember, the derivative of a constant is 0. There's my first derivative. So 6x squared minus 6x minus 1. I'm going to grab red so I can do my second derivative. And my second derivative is just taking the derivative again. So I'm going to take the derivative the exact same way, but now I'm going to have 12x minus 6. If you guys notice, every time that we drop an exponent, right, we've taken a derivative. So when we take a derivative, we drop one exponent. So what started as a cubic, when you took the first derivative, this cubic became a quadratic. And then I took the derivative again, and now I have a linear function. And this is going to come into play a lot when we look at first, second derivatives and the originals when we start to talk about how those graphs play with each other. So we are actually going to be looking at the graphs of all three of these in just a little bit, not quite during this unit, but soon that will come. All right, that's example 1. That's a pretty straightforward one because that's a polynomial. Let's look at one that starts off as a chain rule problem. So my first derivative for this one is the chain rule. It is a composite function. I have an inside function, which is a quadratic, x squared minus 3x. That's my u. And my du, my derivative, or u prime, is going to be 2x minus 3. I also can write my y as u to the, which would make the dy 3 u squared. Okay, so when I come back over to find my derivative, remember it's your dy, the derivative of the whole outside function, multiplied by the derivative of the inside, which is 2x minus 3. And I can put my, at this point I found the derivative. So I'm looking at this 3 and the 2x minus 3, and I'm thinking, all right, I can distribute. So I can write this as 6x minus 9. Keep those parentheses around it though because it's a binomial and it's still multiplying but by what the u is squared. So at this point I can put my u back in, which was the original inside function, x squared minus 3x. I have two choices at this point. One choice is to keep it as a product because I'm about to find my second derivative. Or, since it's only a power of 2, I could try to FOIL this, the x squared minus 3x, and then distribute it to the 6x minus 9, get a really long polynomial, and then take the second derivative. Since we just learned how to do the product rule, I'm going to actually go ahead and use the product rule for the second derivative. So I'm going to choose my u to be the 6x minus 9, and I'm going to choose my v to be the x squared minus 3x and that quantity squared. So if you notice, this entire first factor really has to be my u, and the second factor has to be the v. The entire x squared minus 3x squared is the v. So we're not leaving out that squared because that's part of what your v is, which means we're going to have to use the chain rule within the product rule. So I'm just writing out my du. My derivative of v, I'm going to have to use the chain rule here. So my 2, the power of 2 is going to come down, multiply by x squared minus 3x. Remember, we drop one power, so now I have to the first power multiplied by the derivative of the inside, which is 2x minus 3. At this point, this is going to get really long if I want to keep it like this. So I'm going to go ahead and distribute. And in order to do that, I'm going to go ahead and FOIL these two first. So x squared times 2x, that is 2x cubed. X squared times negative 3, that's negative 3x squared. And then we have the negative 3x times 2x. So that is actually negative 6x cubed. And then we have negative 3x times negative 3, that's positive 9x. All of that is still multiplying by 2. So we'll go ahead and multiply the 4x cubed. And then we have 6x squared minus 12x cubed. And then plus 18x. okay? Once that happens, yeah, let's go ahead and bring the x cubes together as well. So 4x cubed minus 12x cubed. So now I have negative 8x cubed. And minus 6x squared, we'll put it in descending order, and positive 18x. Okay, we just did a lot of work ahead of time before we even have to do the product rule. So you guys will notice that sometimes it is a little bit easier to use one rule over the other. Give myself a little bit more space. It might have saved us some time, right, to FOIL out this product and just do the power rule once you had a polynomial to find the second derivative. Let's see what happens though. So I have my second derivative. I'm going to take my derivative of u, which is 6. Always take the derivative of the first factor that you choose. That'll help you with the quotient rule as well. So derivative of u is 6 multiplied by the original v. So that's our x squared minus 3x quantity squared. And I'm going to add that to the original u, so the 6x minus 9, and multiplied by the dv, the derivative of v that we just found. So that is the negative 8 x cubed minus 6x squared, and then plus 18x. Okay? By doing it this way, you definitely have a lot more that you need to simplify. So as you guys notice, we now would have to FOIL this out, distribute the 6, and then also distribute the 6x minus 9 to our trinomial over here in order to get our final answer. Whereas if we just FOILed this out at the beginning and then took the derivative, that would save us some time. So when you guys go through all these different examples, kind of think in your head, okay, which way would be easiest for me and most efficient for me? All right, so I'll leave that for you guys. So that was 2 examples of a first derivative. What I'd like to take you guys into now is just a little summary, or second derivative, excuse me, of what we're really finding here. You're going to notice that s of t, s is used a lot for displacement. Displacement function just means what is the distance, right? If you guys are walking from the gym to the math hallway, your displacement is how many, basically, what was your distance away from the gym? All right, it does not necessarily count your total distance, which is if you turned and went upstairs and then went in a loop and then went down to the library and then came back around. Your total distance would be much more than what your displacement is. Your displacement just takes from point A to point B, how far did you go? So what is that distance that you just traveled? When you guys are looking at s prime, we're now talking about s prime as your rate of change or your velocity. So we are going to use v a lot in terms of time when we're talking about real life examples for first derivative. And then our second derivative, acceleration, the rate of change of your velocity, we're going to talk about this in terms of a. So anytime that you guys see s of t, that's really talking about your displacement, the distance that you've traveled from point A to point B. When you see s prime, that's really your velocity. When you see s double prime, we're talking about your acceleration. I'm going to take you guys through one example together. Let's back up a second. There we go. So our first example is a car starts by moving from a fixed point A. Its distance s in meters as time t in seconds passes can be written as this right here. So already I'm looking at this s of t and I'm noticing that this is my displacement function. If I want to talk about the speed, I'm going to have to either find my first or second derivative so that I can discuss velocity or acceleration. So let v be the velocity as the car moves from point A. Find the speed of the car. Find the speed the car is moving at t equals 4 seconds. All right, so first of all, I'm seeing this word speed. That means I have to find my velocity. To find the velocity, what I'm really doing is finding the first derivative. Go ahead and take a moment to find the first derivative. So once you guys find the first derivative, remember that you are not only finding it, so this is going to be 4t plus 5, you want to find it at 4 seconds. So let's go ahead and let 4 be our t. And now we are saying that 4 times 4 is 16 plus 5